this is Jack Jackson. In this video, we're going to be looking at some more trigonometric limits, so limits involving trig functions. And they're going to be based on these two limits here that we just proved in our previous video. The limit as x goes to 0 of sine x over x equals 1, and the limit as x goes to 0 of cosine of x minus 1 over x equals 0. And by the way, notice that this first one here, if you did the reciprocal of this, you're going to get the reciprocal of the limit, which is also 1. So if you have the x on the top and the sine x on the bottom, and take the limit as x goes to 0, that's also going to be 1. Now that's not going to work over here because 0 doesn't have a reciprocal. Now these two limits are very important in the steps in the proof of the derivative of both the sine and the cosine function. And so we're going to be getting to that a little bit later in our next video. But in this video, I thought we would just take a look at how we can use these two particular limits to help us find some other limits. Warning, don't forget that you have to be in radian mode to work with any trigonometric functions anytime in calculus. So in calculus, we're always in radian mode. So let's take a look at this example here. Okay. Get a little closer. Okay, so here I have a function, sine of 7x over x, and we want to take the limit as x goes to 0. Of course, if you plug in 0, you get sine of, see, 7 times 0 is 0, sine of 0 is 0, and that's 0 over 0, that's an indeterminate form. Plugging in x equals 0 doesn't help us any. We need to try to see if we can work with this. Well, the trick here is to multiply the numerator and denominator by 7. Now this 7 in the top, I'm going to bring out front of the limit sign since it's a constant multiple. And then I have sine of 7x over 7x. Now if you think of doing a substitution where t equals 7x, this becomes sine of t over t. And notice as x goes to 0, t also goes to 0. So then this limit can be replaced by saying t goes to 0, and that limit, as we've just proved, is 1. And so we get 7 times 1 is 7 for the limit. We can corroborate this with a graph and or a table. So down here I've put this in my graphing calculator, a TI-84 calculator here. And I've done a table where I can put in values, put the kind of table where it asks you for the x's. And I put in x values closer and closer to 0, both positive examples here and negative ones up here. I've got 3 positives and 3 negatives, each getting closer and closer to 0 in the middle. And notice the y's get very, very close to 7. And then here we see a graph which I did in the program called Graphmatica. And you can see that in fact the graph does get close to a hole in the graph there at 0, 7. So we did it algebraically, and then we also verified that graphically and numerically. Okay, let's look at another one. The limit as x goes to 0 of sine of 3x over sine of tangent of 5x. Well, first of all, I'm going to rewrite tangent of 5x as sine of 5x over cosine of 5x using our basic quotient identity for tangent. So, when in doubt working with trig functions, it's often a good idea to just switch everything to sines and cosines if possible. And most of the time it is possible. So multiply top and bottom of this fraction by cosine of 5x to get rid of the compound fractions, and we get cosine of 5x up in the numerator with the sine times the sine of the 3x, and that's over sine of 5x. Now I'm going to break this ultimately into 3 factors here. The cosine of 5x is going to get its own factor. The sine of 3x will get a factor, and the sine of 5x will get a factor. Now notice I put an x in the numerator and denominator. That's legal to do, provided x is not 0. X is not 0, it's only getting closer to 0, so that's okay. So these x's that I introduce here and here balance each other. The 5 is balanced by the 1/5 out here, and the 3 is balanced by the 3 in the numerator out here. So the 3/5, if we multiply this out, the 3 will cancel the 3 here, the 5 will cancel the 5 here, the 2 x's will cancel. We'll be back to where we started. So that's a legit step. We can do that. So now I can use the constant multiple rule for limits and take the 3/5 out front. And then I can use the fact that the limit of a product is the product of the limit, provided those three limits exist. Okay, now the first one here, the limit of the cosine of 5x, that does exist because cosine of 5x is a continuous function. If we plug in 0 here, 0 times 5 is 0, and cosine of 0 is 1. So that works out nicely. Now these two parts are not continuous functions here, but here notice as x goes to 0, 3x also goes to 0. So I might even write that way as 3x is going to 0, and this one as 5x goes to 0. So notice as x goes to 0, 3x goes to 0, and this is sine of some letter, let's say sine of t over t as t goes to 0, that is 1. And this is upside down from that, but the limit's still 1. This is sine of another letter, say w over sine of w as w goes to 0, and that's also 1. So all those 1's multiply together to be 1 times 3/5 is 3/5. 3/5 in decimal form is 0.6. And so the limit is 3/5 or 0.6 if you prefer decimals. Again, we checked it with Graphmatica here, and you can see the hole in the graph right there at 0, 3/5. And we can see that it is 3/5 numerically by plugging it in our graphing calculator and seeing that this is getting closer and closer to 0.6 for y as the x is getting closer and closer to 0. Two more examples. Alright, this one here, cosine of 7x minus 1 over sine of 11x, and take the limit as x goes to 0. So I want to break this apart. I've done a couple steps here at once. Let's see. So I've broken it into factors, introduced a couple things which ultimately cancel out, working backwards, and then broken it into several separate limits. So basically you know what, let me go ahead and add one more step in there so you can see it a little bit better. Okay, so basically we have this here. Okay, so look what we've got. We've got let's just multiply this out, and you'll see that it's where we started. The 11 cancels the 11, the 7 cancels the 7, the two x's cancel each other, and then we have this in the numerator, this in the denominator. That's what we started with. So that's a legitimate thing to do. Now, why do we do all that stuff? Well, we want to break this into separate limits. So first of all, the constant can be brought out front of the limit sign with the constant multiple rule. And then we have the limit of the product of these two things, which is the product of the two limits, provided they exist. Now, notice then here we can think of this as the limit as 7x approaches 0, and this is the limit as 11x approaches 0. So do some sort of substitution there. Okay, and we see that here we are. Okay, that looks pretty good. Okay, so what we have here is, that's not the right one. Where are we? Here we are. Okay, now we got it where we need it. Okay, so back to where we were here. Notice that we want this to be cosine of something minus 1 over that same something. So cosine of t minus 1 over t, where t is 7x. Notice as x goes to 0, the 7x, or the t, goes to 0. And so this limit is 0. And then this one we want it to be, pick a letter, u over sine of u, where the u goes to 0. Notice as x goes to 0, 11x, or u, goes to 0. So this goes to 1. And of course, since it has a factor of 0 in here, doesn't matter what the rest of it is, we multiply all that together, we get 0. So this is going to have a hole in the graph at the origin. As x goes to 0, y goes to 0. And you can see the hole in the graph at the origin right there in the graph in Graphmatica. In the graphing calculator, we put this in for the formula in for y. Remember, we're in radian mode. And we pick x is closer and closer to 0, and we see y's are also getting closer and closer to 0. Okay, let's look at one more example. In this example, we're taking the limit as x goes to 5 halves of 4x squared minus 16x plus 15 over sine of 2x minus 5. At first glance, that doesn't look too much like what we had before. But if we factor the numerator, we get 2x minus 5 times 2x minus 3. So we can think of this as sine of something, and we put the same something up there. Luckily, we already have it. If we didn't already have it, we would plug that. We would actually just multiply the numerator and denominator by the 2x minus 5 at this point. But since we already have it there, we could break it into two limits here. The 2x minus 5 over the sine of 2x minus 5, make that one part, and the other part is the 2x minus 3. Take the limit of both of those things. Now, here, as x goes to 5 halves, notice that 2x minus 5 is going to go to 0. So this is like t over sine t, where t goes to 0. That limit is 1. And of course, this linear function is just continuous, so we can just plug in the 5 halves in place of x there. The 2's cancel here, so we get 5 minus 3 is 2, times that 1 is 2. So the limit is, in fact, 2. So 5 halves, comma 2, or 2.5, comma 2.5, comma 2 is a hole in the graph right there. You can see it in Graphmatica. If we plug this in as the original and look at our graph, at our table in the calculator, this time we're letting our x's getting closer and closer to 2.5, but not actually be 2.5. If we actually put in 2.5 here, we would get an error message. This is actually 2.4 with a bunch of 9s. This one here is 2.5 with a bunch of 0s and a 1. They're not exactly 2.5, but the y's get extremely close to 2. And so there we go. So that gives you a couple examples of, 4 examples of how we can use these two basic limits here to, in turn, compute some other limits. But these two limits here are particularly important, especially not only for just finding some limits like we did in this video, but for finding the formulas for the derivative of sine and cosine, which we're going to do in our next video.